just declare this, declare a victory on, multipole expansions. And let's move on to the next big part of what we're doing, which is magnetostatics. Okay, so again, this is going to be a little bit different from what we had before, but let's just see how far it can go. It's going to be, again, stuff that you've become familiarized with in your earlier courses, so I'll try to go relatively quickly through all of that. Okay, so magnetostatics, we're talking about magnetic fields, and magnetic fields you detect by their effects on charges, on moving charges. And the fundamental relation that you're interested in here is the Lorentz force. You know that a charged point particle moving at a certain velocity v in the presence of a magnetic field will feel a force Q with V cross B. Yeah, so the force is actually perpendicular to both the motion and the magnetic field. So this is, again, an experimental fact that's just been detailed, throughout history. It has lots of fun effects. One little example of that in the notes is about cyclotron motion. So what you have is, imagine a magnetic field that comes out of the page like this, and you've got a little particle moving at a certain velocity v, like this. You see, so or I got no, actually, I'm moving the field into the page. So the field is going into the page. So if I do v cross b, the force is going to be like this. But if the force is like this, there's going to be a deflection towards the left, and then there's going to be circular motion. So this particle is going to start doing orbits that are called cyclotron orbits, whose relationship or whose size with respect to the field and the other parameters of the particle you can easily determine by just equating centripetal and centrifugal forces on that thing. So the centripetal force is just coming from the magnetic field here. The centrifugal is just, mv squared over r. So what does that tell you? It tells, so if I equate the strengths here, so Q times V times B is the strength of the force coming in. And then this has to equate the centrifugal force, which I'll just write as mv squared over r, where r is the radius of this motion here. So what this tells you is that the momentum of this mv this is just Q times B times R. So that's how you can, with a known magnetic field, for example, look at the charge of particles that move around. So in the early particle acceleration, these bubble chambers that they had, particle detectors, you see all these round things in there. Then they knew the field, they checked the radius, that gave them an idea of what the charge was for these things. So there's a cyclotron frequency associated to that. It's in the notes, it's simple physics, but I'll let you have a look at that. That's one of the first effects of this thing. An important characteristic of the Lorentz force is that it acts perpendicularly to the motion. Therefore, they don't do work. They don't do mechanical work, because that would require a component along the motion. You have to be a bit careful how you state that thing precisely, but now for a point particle in that circumstance, that's the case here. So these magnetic forces don't do work on this particular object. Okay, so again, this is stuff that you'll be familiar with from your first course. Now, what we'd like to do is to make some general statements about what happens in space and time when we've got charges floating about. And for that discussion, we're going to imagine that our space is filled with currents moving back and forth. And we're going to try to characterize these things. So we imagine that in our space, there is a vector that will represent as J, which is a current density. And how do we think about that? We think about that by using imaginary little cross-sectional areas through which we measure the flow of charge. And what occurs in a certain amount of time, delta t, is that a certain amount of charge is going to go through such a little surface. So if you imagine that this is a tiny, tiny little thing, the spatial variations of that current density are unimportant. There's just a certain flow of charge going through this. So in time, delta t, a charge delta q equal to the following thing. So I would have my current density J. I would take the dot into the unit normal vector of this little differential surface area delta S in there. So because of course, if the current is perpendicular to the surface, there's nothing going through the surface. So I'm just interested in the component along the normal to the surface like this. And then it would be proportional to the area itself, delta S, and to the amount of delta T. Okay, so it goes through.